First of all, thank you everyone for making it. Appreciate you taking the time to be able to be here. Let me introduce myself. My name is Arvind Sriram. I'm an architect for Adobe. So we use FoundationDB. We have for the past couple of years, and we've been talking about doing a meetup series to sort of bring together people who work on FoundationDB or people who use FoundationDB to share their knowledge and to learn from each other. So that's the goal of this whole meetup series. And we're going to have this as a monthly series. We will have one or two speakers every month come and present some use case, a product that uses FoundationDB, or it could be someone who works on FoundationDB and they will deep dive into some technical aspect of FoundationDB as a knowledge share series. Right? So that's the intent behind this. So our first speaker today is Chaudhary. He's the co-founder of Tigress. It's a startup. And he has previously worked at Uber. He's worked on distributed systems at high scale. And he's going to give us a glimpse of how Tigress uses FoundationDB. So with that, help me welcome Himank to the stage.
So I'm Himank. I'm co-founder and CTO at Tigress Data. And prior to co-founding Tigress with my co-founders, and Ovis is also sitting here, he's one of the co-founders as well of Tigress. So prior to co-founding Tigress, I was tech leading a product called Docstore at Uber, which was a distributed transactional database, globally deployed, and was serving majority of Uber traffic, Uber rides, Uber Eats, any product that Uber has. And at the peak, it was serving tens of millions of QPS and serving tens of petabytes of data. Some of the publication also highlighted in this slide, but it was mainly related to how we build our application, how we build Docstore, how we build the eventing framework for the Docstore, which was how the real-time events were flowing out of the database. Now, coming back to the talk, today's agenda is that first I'll be introducing Tigress, we're building. The second would be like how FoundationDB fits in our architecture. Third will be high-level architecture, showing all the high-level components and FoundationDB in it. Then a topic on asynchronous queues, secondary indexes, and global replication, and then finally Q&A. So what is Tigress? So Tigress is a globally distributed object store that allows user to store and access their objects with minimal latency across the globe. So with Tigress, in a nutshell, the idea is that you don't need to worry about your having the CDN or caching or replication, but you have a global object store, which you would be using, that provides out-of-the-box minimal latency for your objects. If I summarize that in the four features that are highlighted in these slides are that a single global endpoint for your object store, you just use that global endpoint to access objects anywhere in the globe. It's S3 compatible, so as long as you are aware of S3 APIs or you're familiar with AWS S3 tooling, libraries, then it's just about replacing the endpoint with Tigress, S3 endpoint with Tigress endpoint. Store data near user. So the idea there is that it's a global distributed system. And when we receive the writes are getting stored close to the user. So what that means is, let's assume that you have a global application. That global application is deployed everywhere, and now you have users writing objects from New York, and they are writing objects from Sydney. So if you receive write from New York, then objects will get stored near New York, near East Coast. And if you receive write from Sydney, then the objects will get stored near Sydney. So this automatically provides a nice property to your application. Like if the read happened for those objects close to the request made during the write, then it will automatically provide you with minimal latency because it guarantees that the objects are closed where they are getting accessed. But now it can happen that you have objects written in East Coast, but you have read access from Sydney or West Coast or anywhere else. Then what we have done is that we have we have implemented caching layer as well. So we automatically move objects around based on the access pattern. So one of the access pattern is the caching, that we move objects based on when we see that the request for these objects are coming from different regions. So to optimize latency, we move the objects near the region where the requests are getting made. So this automatically ensures that this provides low latency during access. And last but not the least, fast small object retrieval. So this is we have also done a bunch of optimization on how you can access small objects at close to Redis speed. We have multi-tiered caching architecture, which allows us to provide this functionality that small objects can be retrieved very fast from the system. So in a nutshell, if you see all the points that we have highlighted will ensure from the user perspective that they don't need CDN caching or application, and Tigress will automatically manage all of them for them. All of this for the users. Now coming back to building on FoundationDB. But a quick recap on FoundationDB. So like how Arvind was highlighting this, just the same few majority of the points about the FoundationDB. So FoundationDB core data model is it's an ordered key value store that offers a strict serializability and provides ACID transaction. And the good thing here is the transactions are multi-key across shards. There are no restrictions. So this provides very nice property as an application or as a user that you just start the transactions, use it, and then just commit it without worrying about where the key lives and so on. The second point here is, and it's very important to us as well, that apart from storage and retrieval, it doesn't interpret the data. So FoundationDB doesn't provide any indexes, doesn't provide any schema, or doesn't have any concept of tables, structured query language. It just provides low-level building blocks like replication, HA, sharding, transaction. And when we were starting Tigress, this was very important for us because we wanted to use something which provides low-level building block so that we can implement or we can control the functionality on top of it. We want to have some custom functionality, but we also don't want to database to again implement those functionality because that will be redundant for us. But in the same context, we also didn't want to reinvent the wheel. We also didn't want to again rewrite whole transactions when some open source database already offering us that. We also didn't want to reinvent this strict serializability, which would be very hard to re-implement and will take a lot of time. And same applies to sharding or HA. So in that context, we wanted something that can provide us low-level building block on which we can build higher level components. And that's where FoundationDB fits perfectly for our use case. And this is one of the reasons primarily we are using FoundationDB. Next, it's quite mature, used by multiple companies, used by Apple, Snowflake as a building block for their cloud infrastructure. In fact, now Adobe is using it, Datadog uses it. So it's multiple companies are using it as part of their infrastructure. And the last point here about FoundationDB is that with any distributed systems or distributed storage, one of the key property is how to convince your user or how to convince the consumer of these distributed systems that whatever you have written is working as expected and there are no corner cases to it. Because with distributed systems, there are a lot of races, there are a lot of concurrent issues, there are a lot of isolation issues, transaction issues. But with FoundationDB, they have a thorough simulation testing. And in fact, the Jasper distributed testing framework has claimed that FoundationDB simulation testing is much more comprehensive than Jasper itself. So this, and there are no other database or distributed database out there that has such comprehensive distributed testing. So from that angle, it was also safe bet that we understand that the promises that is made by FoundationDB is actually what they are offering as well. But then what Tigress has built? So Tigress has built a scalable metadata storage engine. And when I say metadata storage engine, it's basically a metadata storage layer, which we have implement on top of FoundationDB. So metadata storage engine, we call it a layer, that storage layer plus the FoundationDB. So this metadata storage layer exposes low-level transaction primitives to our internal services. And these internal services then use this metadata storage layer to store all the metadata of Tigress. That metadata includes object metadata, bucket metadata, user metadata, or any metadata that you can imagine in the system itself, all gets stored in FoundationDB. Then a query engine. So FoundationDB itself doesn't have any query language, and Tigress supports querying with comparison operators that you can use on the user metadata that is stored with objects. So for that, we have implemented query engine or query layer inside this as well, which is responsible for processing the query, creating the query plan, executing the query, ensuring the query is optimized, and then executing against the FoundationDB. Indexes. So we have implemented secondary indexes. So secondary indexes, this metadata layer that we have is also responsible for managing all the indexes. And these indexes are user-facing indexes. User can define those indexes. And basically, when users write any object in Tigress, they can write user metadata along with the objects. And on that metadata, they are allowed to set secondary indexes, or they are allowed to create secondary indexes. And these indexes is the responsibility of this layer, that when we are committing the metadata of objects, then we need to make sure that we also commit the indexes associated with that object. And as this is happening in a transaction, this provides a nice consistent properties for these indexes as well. The next is related to how the data layout is done for all these metadata objects. And this is not only related to metadata objects, but any metadata that is getting stored in FoundationDB. So as FoundationDB, data layout is just key value and it's just bytes. But what we need is we need to have some information about these keys when they are getting stored in FoundationDB. So what we have done is we have added information about users, bucket, type of metadata that we are storing, index, keys in the key itself. Now, if you store everything in that key, then the key will become very big, and that will impact the performance. To work around that, we have done dictionary compression on the keys itself. So all these IDs or all these names maps to some integer IDs that are encoded in the key. Same applies to values. So values are also protobuf encoded. And the reason being, we also want to control many things on the objects. So we support compression or not, but we have compression and we have chunking as well. And everything is driven on the object values by object value only, because the value is encoded and value has all this information that we need. And these are forward and backward compatible both, because when you have that information in the value, for example, for compression, it is encoded as part of, it is present in the value. So when we read it, we know whether the object that gets stored, whether that is compressed or not. And based on that, we can decompress it. Same applies for chunking. So if the key has chunked, if key has chunk number, then we know that this data is chunked. So we need to merge it back and then return it to the upper layer. Global replication. So this is mainly that we have multiple FoundationDB clusters and we have our own replication for HA purposes. And there are different geographic regions where these different FoundationDB clusters are deployed. And last but not the least, the operationalizing FoundationDB, running in the production and have all the monitoring and everything in place. Now, high-level architecture basically wants to show where FoundationDB is fitting in this picture. So Tigris has a composable architecture. So everything, compute is disaggregated from storage. And in fact, all the components are disaggregated in the sense that allows us more control in terms of how we can scale each component. So for example, compute is separate, storage separate, and storage further is divided into large objects versus metadata. We have a different caching layer, which again is scalable differently, and then the compute. So now in this high-level architecture, we can see that there is a metadata storage, and that's where this is our metadata storage engine, which is running, which has FoundationDB clusters, and on top of it, we have the metadata storage layer, and this whole we're calling it metadata storage engine. Now, more details about this metadata layer. So, for example, handling of write request. So, we are leveraging the nice property that FoundationDB provides. It's already, we know that it's strictly serializable and it supports ACID transactions across the key space, multi-key cross-shard. So we are using it, but we have our own small transaction layer that wraps all this transactional functionality because we also support explicit transactions. And these explicit transactions are basically the services that are calling this metadata layer can open up transaction and perform a bunch of operations. So that's where this transaction layer is, which maintain all the sessions. Whether if it is explicit transaction, then it manages all these sessions. If it is implicit, it will simply start the FDB transaction. Then we have writes and reads layer, which is responsible for handling differently writes versus reads. So write layer, for example, is responsible for handling all the indexes that we have. So in the write, we can see some of the steps that are done as part of write-only transaction, where we build all the index row corresponding to the object, we write all these indexes row, then we write main table rows, and then we commit the transaction. If it is implicit transaction, we retry if we know that it is retryable. But if it is explicit, we will let the caller service retry the transaction, and we just simply return the failure to the caller service.
Within this picture, where does the actual write to the large objects?
So that is the calling service. So when the calling service is sending the writes to this metadata storage engine, it has already split the objects. It has already split the block, and then only the metadata is sent to this guy.
So the logic for controlling the location of the object write is independent of this metadata write, or?
So think of it as a coordinating service which receives the user request and it has the writes. Now for that particular write object that we have, we split its metadata and block. So block gets stored in the block. The block storage first. Then we have some metadata related to block. We attach to this with the user metadata, and then we send it to this guy, which is the metadata storage layer, then writes the metadata to it. Does that make sense?
Which okay, but yes, but that implies that the split actual data portion could be written independently.
Yeah.
Of, got it.
Yes. So this is just managing the metadata completely. So for read, we support some complex query operations on the read query, and again, these complex operations are on the metadata of the object. So on those indexes, user can perform the queries. So read-only transaction is basically when the metadata layer receives this query, it basically generates the query plan, figure out whether this query can be handled by a single index or it needs result from multiple indexes. Prepare this index reads, hit FoundationDB with range reads or point reads, depending on the query plan. Read row, and as FoundationDB client automatically supports streaming, so we also support streaming and to the calling service as well. As we are gRPC, so we just keep getting data from FoundationDB and we keep streaming out to the calling service as well. This is a typical handling of a read request. This is the detail about the data layout that I was talking about. So it's basically showing that all the metadata is getting stored in this FoundationDB, and we have a different metadata subspaces inside this FoundationDB. And basically think of it as just different tables. So different tables for some buckets, different tables for managing tenants or the users that we have, and then one whole giant key space for managing all this object metadata. So on the right, the key basically it's showing is that it has the tenant ID, which is an integer, then bucket ID, then index identifier. Index identifier is basically telling us what type of index it is, and then index value, and that points to the value. And then value is again protobuf encoded, but has all the information related to the objects that is getting stored. Its encoding, its compression, timestamp, and then raw data, whatever we are storing chunk. And then anything that is more than 100 KB, we automatically chunk it. And then each chunk is tagged with a chunk number. And same applies to compression, that we compress and then we write. Chunking, when we read it back, if it is ascending reads, then it's fine, we just read. But if it is descending, there is some extra handling to make sure that you merge those chunks back because you're descending in the descending order of the chunks. Secondary indexes. So this is more visual representation of what is happening in the system. So we have user metadata, and user metadata, let's assume it's just JSON. And user wants to have a secondary index on name. So all the values, so the secondary index that we have is the key is whatever they are indexing. And the value is just a pointer to the main table row. So we are not storing the value again, but we are just managing the pointer to the main table row. So which means we need to do an extra read, but it's optimizing the storage. And it's using FDB transactions for indexing object. Anytime we see any mutation on the objects, we do this. The design is extensible to can also support unique indexes or compound indexes. In fact, unique indexes is very easy because of FoundationDB, as we already reading the data to clean up the old indexes. So we can also check uniqueness, and here we can use the strict serializability because it guarantees that if we are reading something and it's not present, then it guarantees uniqueness. And this is some of the functionality that Tigress supports. So Tigress supports all of the following comparison operation on user metadata. So it supports equality, not equal, greater than, less than, combination of and or. Then user can also do order by to sort the result set and so on. The replication. So what we have, so the layout of metadata clusters is done in a way that for one geographic region, we have multiple FoundationDB clusters deployed. And these clusters are replicated by an async service that is deployed outside of it. But we are again using FoundationDB to store all the transactions that needs to send out to the remote FoundationDB cluster. So basically what is happening is, so whenever the write is coming to a single FoundationDB cluster, let's assume the first cluster as region A. And in that, when the write comes, we perform all the transaction. And in the transaction itself, we write all the entries that needs to be replicated in the queue. And this queue will then be used by this external service, which will read from this queue, and that item itself has all the information where it needs to send. And that information will be used to send it to the remote regions. So this is how we have a global replicated FoundationDB. It's asynchronous, but we have multiple clusters in each geographic region. We have in US and then we have in Europe.
Sorry, so the replication is through some Kafka or something?
No, so we are using FoundationDB itself as queue. And then the asynchronous framework or the queues that we have. So what we have is, so we have implemented the Apple's quick paper, but the basic gist is that we have a queue, and the queue is already ordered because FDB has key value ordering already. So any event, so we have different tasks, and all these tasks are managed through different queues. These tasks go to these queues, and we attach a timestamp to all of these tasks. And then there are workers who are going through these queues, pulling the task out and performing the task. For example, one of the tasks that is based on this queue is replication itself. All the replication events are going into the queue. Then we have a bunch of workers reading from the queue, understanding the task, and then doing the task of sending the events to remote cluster. Same applies to if we need to do backfilling of index, like if user adds some index after creating their bucket, same applies to this as well. And again, the same queue will be used to add an event and then dispatch the events. So that's all I have. Happy to answer any other questions that you guys have.
So the wall clock is like a watermark?
Yeah.
Just one question. You mentioned the geolocality, right? So is that encoded in the index that you maintain, and then that index is globally distributed? Is that how we know that the key is local versus?
So that, yes. So that is basically stored in the metadata of the object. And anytime the write comes, we have all this information, and basically we call it like placement information of the object. And we also have metadata as through replication, we have deployed metadata everywhere. So when we read, we get the metadata, and out of that we know that, okay, where exactly the object lives so that we can fetch it. And then we can again do all the things like caching it, moving object around and so on.
So metadata is globally distributed, and then the actual data payload is not, and that's why you.
But that is also dependent on if it is cached at multiple location and if we can access it at close by location or not. If not, then we have to fetch it somewhere else. So there are also multiple strategies that we use. We push it to different continents. Sometimes we push it to multiple locations as well, depending on the access pattern.
You mentioned Fly.io as your infrastructure layer for edge, right? So when you have globally distributed DBs, do you consider them as sort of an edge, or is it like a hub? And then how do you integrate with Fly.io's? Like Fly.io itself does sort of edge routing, right?
They have, and it's globally deployed.
Yeah, so we don't think of it as edge. We think of it as, this VM as a service. They provide us with machines similar to EC2. And we rely on their global load balancing to route the request to the closest location. So if they have 38 locations, 38 data centers, we have 38 data centers, and they have a global load balancer. When it receives a request in Sydney, it routes it to the nearest POP or the nearest
So
data
you
center.
do the M by N, where Fly has a lot more edges, sort of, and then.
I wouldn't say it. Edge is a very overloaded term.
Sure.
My phone is also an edge. I wouldn't call it an edge. It's just like a data center.
Okay.
Yeah, just call it data center.
I have a question from online. How did FDB's testing, simulation, and verification philosophy affect Tigress's engineering culture and product culture?
So it affected, I mean, it is one of the key consideration when we were deciding whether we need to build something, use something from outside. That was one of the key consideration, because we saw that and we realized that this is one of the topmost simulation testing that they have already claimed that they have done. And even if we, let's say, if we take a back step and if we write something, we still need to prove and go till that point to show to the world or our customers that, okay, that the system is tested through all this simulation testing that we have done, and which FoundationDB has already done. They have whole talks about it. So that is definitely one of the key consideration of choosing this product, that, okay, this part is already claimed that they have strict serializability, whatever they are claiming, and they are actually proven that as well.
I also have a question of my own. I'm wondering if you could talk a little bit about Tigress's customers, like at a high level, like what some of the use cases are that are making use of the Tigress product.
So any AI workloads, we have AI workloads, we have some workloads that want low latency access. They have so apps that run inference, they are using us because they have data models that have already generated now images or videos, and now they want to dispatch it globally, and they want to make sure their user can access all these inference data as fast as possible. For them, they are using it, then there are multiple apps who wants low latency access, or many applications that don't need to worry about like managing replication, or they just want a good developer experience and has global application as well. So they have global access. So they are using us. I don't know if you want to add anything there.
I mean, there are all kinds of users, so analytics use cases, asset storage, AI use cases, there are all kinds of use cases. There's not one. We're also trying to learn
Yeah.
who is using us most. Yeah.
So you mentioned the coordinator service which splits the data into metadata, right? So I'm assuming that you might have some orphans or something which when the metadata right fails or either one of them fail. So do you have like a background job which cleans these or?
Yes. So the queuing framework that we have. So we schedule periodically jobs, and we call them garbage collection. And these jobs basically understand the global view that we have versus the block view, and then periodically try to clean up any orphan blocks that we have.
Okay, if there are no more questions, I think it's a good segue to the next talk. Thank you, Himank, for a great talk.